Yeah, I was looking right now for job, but then after I turned like finance or trade, and then I found there's nowhere else to stay.
See the time?
Huh?
You don't see the time? Oh, yeah. Dude, who's in there? He's still playing. Well, yeah, he was later. Bro, that's literally what, the violence is. Bro, what are you? Yeah, better than a weekend. I mean, yeah.
Oh, wait.
I think it could happen. Yeah, it could.
Yeah.
I don't think they should. If anybody should, other than, alright, it's probably Tuesday, Wednesday, or, I don't know,
You know what, I actually hate
I think they lost the best. Oh, no, the other day,
I think it was
their second.
Yeah, I'm just gonna project it.
Oh, yeah. One of the last years, yeah. Like, honestly, that one, like, one of the last years. Would have been a different video, so allow us to, like, yeah.
Okay, let's start. So, anybody wants this handout which I gave last time? Okay, so for those people who missed or the first time introducing you to DH, this is another example involving DH. I'll do this example and move on to other things. So let's do another problem using this handout. Okay. If you forgot a handout, I don't have more handouts. I actually have posted the handout in my previous class. You can view it if you want to read it and follow as I solve this problem. So the question is, for this manipulator, as I said earlier, we do not anymore show the links of the manipulator, we just show the joints, and that's just to remove clutter from the image. This is a 3-link manipulator, and it is not planar because you can see that the axes are along the axes of the manipulator are not along the same direction, but this one is that way, so it turns this way. The other revolute joint is that way, so it's going to move in 3 dimensions. Okay, so it's a 3 degree of freedom, revolute only manipulator. We need to find the position and orientation of the end effector. That's the point about which you put the tool, which will do the work, lift something and so on. Okay, so let's go through this. So there are 3 steps. First step is assign coordinate frames, which I'll just do. We copy paste this image first. So let me do it on a new page. Okay, let's start assigning coordinate frames. Okay, so assign the first step, assign zi along the axis of actuation, and do this for each link. So there are 3 links or joints. We assign z along those axes. So start with z0. Z1 and Z2. Next step is assign the base frame along, that is the frame attached to Z0. For that, we have to first assign where it says attach X0 arbitrarily. Okay, so Z0 is that way or upwards, and we can assign X0 in any direction we want. It has to be 90 degrees. That's the only condition. So any direction in this plane. Okay, so what I did was I assigned it in this direction. Okay, but you could assign it that way, that way. It's really up to you. No problem. All of those are valid assignments. Okay, then assign Y0 such that Y0 is at right angles to Z0 and X0. So you can see that Y0 should be that way. So when you do X cross Y, you get Z. Now it turns out that Y0 or Y1, Y2 is not at all important when we generate the table. Okay, so if you don't want to have too much clutter in your figure, then you can just ignore assigning Y0, Y1, and so on. Okay, you'll see that we never used the Y in any of our formulas. So I'll skip that, but Y0 would go that way, so that X cross Y will give you Z. Okay, so next step, number 3 on first page, assign. We need to assign frames. Well, we need to assign X1, X2, and so on. In order to find X1, we have X0, we need to find a relation between Z0 and Z1. And we have 3 options. Zi minus 1 and Zi are not coplanar. That is, basically they are not in the same plane. That's clearly not the case. In fact, I don't think we have any problem involving case A. It's usually going to be B or C. Zi minus 1 is parallel to Zi. So Z0 is that way, Z1 points that way. Clearly, they're not parallel to each other. Zi minus 1 intersects Zi. So they do intersect, because if you stretch this, it actually intersects that point. So it belongs to case C, 3C. So when that happens, Xi is chosen to be normal to the plane formed by Zi minus 1 and Zi, which means, translating in this particular problem, it is X1 is going to be at right angles to Z0 and Z1. So Z0 is that way, Z1 is coming out of the plane of the paper. It has to be at right angles to that. So we need to find a vector which is always the tip of the pen is the direction of the axis. So Z0 is upwards, Z1 comes out of the plane, and X1 is going to be at right angles to this. Okay, so there are only 2 choices we have. One is it's that way, other choice it's this way. But those are the only 2 choices which make that line 90 degrees to this and 90 degrees to that. So only 2 choices, and you can choose either of those 2, this one or this one. Yeah.
How do you know that Z0 and Z1 are kind of aligned, like they intersect?
So how do you know how Z0 and Z1 are aligned? So Z1 is pointing out of the plane of the paper, and Z0 is like this. Really, it's just a line, it's a ray, right? So it's going to intersect. I drew it short, but it's really an axis which just goes, so it's really this. I just drew it like this, but really they intersect.
What if like Z0 is a little bit to the left?
Then, yeah, so if it is a little bit to the left, then it clearly does not intersect.
So how do we know?
In this case, okay, how do we know? Well, I showed you L1, and I made sure that everything is in the plane. If Z0 and Z1 was not in the same plane, then I would have a hard time drawing it, but I would probably show you, it's really hard to imagine, but I would probably draw, instead of drawing a planar figure, I would draw a 3-dimensional figure, and I'll show that there's a distance between this plane and this axis. So I'll move it slightly up, and it'll be 3 dimensions. So there'll be, it's called an L0, L1. So in this case, since I've not shown anything but L1, it means that those 2 are in the same plane. Okay. Okay, so as I said, there are two choices, Z1, Z0, that way or this way. The one which I chose in my notes was, I chose X1 to be in that direction, okay? But that is just arbitrary, could as well put it the other way. Let's put X1, okay? Next we go to X2. So again, we need to find a relation between Z1 and Z2. Z1 points out of the plane of the paper. Z2 also points out of the plane of the paper. And so they're both parallel to each other. So if they're parallel, this is case 3b. If they're parallel, then what you do is there are infinitely many normals to these two lines, right? If you want to make a life simple in terms of the table, then you want to choose X2 such that it passes through the origin of the previous axis. So if you draw it this way, for example, it will actually pass through origin of 1 or O1, if not written on O1. So I would choose okay, that is one of the two choices. I could have also assigned X2 to be going that way, which would also be a fine choice because it still is along the normal or perpendicular to Z1 and Z2. So two choices, I chose that one, but that is one of the two choices. So at this point, we are done assigning all Z's and all X's. You could assign Y's, as I said, but it's not important. We're not going to use it anywhere in solving this problem. So last step is number 3, end of the page, end effector frame. We need to attach a frame to the end effector. And the simplest thing you can do is assign Z3 for the end effector to be along Z2. And assign X. So again, you can find a relation with Z3 and Z2. They are parallel to each other, which means you need to find a line, draw a line perpendicular to the two. Your simplest choice would be such that X3 is along X2 or it passes through the origin. So this looks a little bit weird. Let me move this so there is no ambiguity in. The intention was to draw it such that that point E is exactly along the origin of that. Now, if it was not, if it was slightly off, then in that case, you would still have X3 to be pointing that way, but I would have given you the distance between that point and this along the Z-axis. That's not given, which means that it's in the plane of Z2, well, Z2X2. Okay, so that completes assigning axis. Move on to the next part, creating the DH table and filling it up. This is step 1. Next step, link I. 1, 2, 3. The 3 pieces AI, alpha I, DI, theta I. Okay, and this is just for me to make, this is something which I do so that it makes it easy for me to put the numbers in the table. Sort of a mnemonic for me to remember how to assign these A's and alphas and D's and thetas. Xi. Okay, I'll explain this in just a bit. Zi minus 1, xi and, sorry, x. Okay, so let's start filling this up. First 4, these 4, and those 4, and then last. So to fill up the first two, we'll look at this thing. It says A is the distance, alpha is the angle, B is the distance, theta is the angle. So to find AI, or in this case A1, because I is 1, we need to find the distance between, put I equals 1. So distance between Z0 and Z1 along X1. Let's go to the figure. Z0 is upwards, Z1 is pointing outwards. We need to find the distance between those two axes measured along X1. X1 is that way. Right? So we look at the distance between this axis and this axis from top, because we want to see the distance along this axis. Since the distance between the two is 0, because they have a common intersection, the distance is 0. If the axis was there, if Z1 was over there to the right, then the distance would not have been 0. So distance is 0. Next is the angle between Z0 and Z1 along X1. So Z0 is that way, Z1 is this way. We need to find the angle between Z0 and Z1 along X1. Okay. So if you curl your fingers from Z0 to Z1, the angle is positive 90 because my thumb points in X1, and so the angle would be 90 degrees. So pi divided by pi. What is very important is that you go from Z0 and Z1 and not the other way. Don't switch. And that's why I wrote it Zi minus 1 and Zi. I did not write Zi and Zi minus 1. You need to stick to that. If X1 was pointing to the left, not to the right, which is also, as I said, a convention you could follow, then this will just be minus pi divided by 2, because now X1 is that way, and so you need to go from there to the angle would have to be well, it has to be negative, right? So since X1 is that way, you'll have to curl the finger this way, but that is not X1, this is X1, so it will be minus pi divided by 2. You could also write it, if you like, you could also curl it this way and say that the angle is 270 degrees. You could put 270 here. That is, of course, if X1 was that way, and that would also be a fine choice. You'll get the same values for you'll get the same end effector coordinates if you do that. So that's also, you could either put, if X1 was that way, the left, then you could put minus pi by 2 or 3 pi by 2, which is 270 degrees. Both will give the same answer. Okay, let's move on to D1. So we look at this line. It's the distance between X0 and X1, the left pi equals 1, measured along Z0. So X0 to X1 measured along Z0. So X0 is there, X1 is right there, and we want to find the distance between the two measured along Zi minus 1, so Z0. So we want to find the distance between these two, and put that along this axis. So it's literally that distance. So it's L1. X0, X1 along Z0. So L1 and then the angle between X0 and X1 along Z0. Okay. Now if you look at the figure there, it looks like the angle is 0, right? This is on top of this. The angle along this is 0. But that is for this particular position. We are looking at a generic theta. Okay. Theta 1 is 0 for this particular configuration, but when the manipulator moves, theta 1 is going to move. And so if you write 0, that's only going to be this instant. In reality, X0 will move. So the angle between those two is going to be theta 1 and not 0. If you write 0 there, it will no longer be a manipulator of 3 degrees of freedom. You lose 1 degree of freedom. So you should put, each line should have one variable, which is the degree of freedom. So in this case, theta is the degree of freedom. It should show up. Okay. So it's really doing this very slowly. I would speed up a little bit now and finish the last two lines. Next we go to 2. So I put I equals 2 in the first line. So distance between z z1 and z2 along x2. Okay. z1 and z2. z1 is pointing out the plane of the paper. z2 is also pointing out the paper. We need to find the distance between those two along x I equals 2. So along x2. So x2 is in that direction. So it's going to be L2. Then the angle between z1 and z2 along x2, since they are parallel to each other, the angle should be 0. Alpha is 0. Okay, next, the distance from x1 and x2 along z1, because I put I equals 2. So x1 and x2, x1 is to the right, x2 is to the right. The distance between those two along z1, so it's 0, because the z1 is pointing that way. If I see it along this direction, the distance is 0. If it was not parallel to each other, intersecting, then it would not be 0. It's 0. And then finally, the angle made by x1 and x2 along z1. Right? So this is 0 at this instant, but in general, c1, the joint 2 rotates, so it's going to be theta 2. Okay, now you see, if you notice carefully, z1, z2, the way this is set up is very similar to the way the other two are set up. So it's going to be the same reasoning. That picture looks so much, the image, the axis z1, axis 1 and axis 2 look so similar to 2 and 3 that you will have the same reasoning to fill this up. So you don't have to actually do this work. It's the same, but with 3. So 0, 0, theta 3. So really what happens is when you have planar, like theta 2 and theta 3 are in one plane, it actually boils down to something very simple. The moment you have something which is at right angles to each other, then you see this factors coming up. Okay, so let's do the final step. In order to find the coordinates of the end effector, first we accumulate the A's, and this is the formula I written down. Yeah, it's also on this page. What I do is I put the first row inside this formula I wrote down for A to populate A10. Then I use the second row to populate A21. And then finally A32 from the third row. Where C1 is cosine of theta 1, S1 is sine of theta 1, and so on. Okay. And finally, we need to find A30, which is A32, A21, A10. Okay, now that's going to be a lot of numbers and it's just not worth writing down a generic formula. I would not do it by hand. I would use symbolic manipulation in Matlab. And if you're told to write this, you would just put it in Matlab and get the answer. So this is what will come out. There will be an R3 and there will be a D3. And the end effector position, E position, is simply the 3 elements in D3. And the orientation is the matrix R30.
Excuse me.
Yeah.
So it should matter the order from, you put A2, 3, A1, 2, and A0, 1. Does that matter?
The order? Yes.
Because
Oh,
latencies.
Did I switch it? I think I
Okay.
switched it. My bad. Yeah, that absolutely matters. You'll get a totally different answer. This is incorrect. It should have been. Good catch. Yeah. Don't switch it because that's a different convention altogether. Yeah, that's right. Okay, any questions? Okay, so I'll have homework where you'll do this for 3 different things, and hopefully that will give you some practice. A manipulator using Matlab. Okay. The key thing is a command which you've probably used in your animation. It's called line. So if you're given coordinates of 2 points in 3-dimensional space, for your homework you only did 2 dimensions. You can take 3-dimensional points, join them by line. That's all you've got to do. So we'll use a command called line. Matlab. Okay, and the syntax, you could check help line, which will give you more information about line. What you got to do is you got to give it the x and y coordinates and of course the z coordinates of the 2 endpoints. And there are other things you can give, like the color you want the line to be and so on. I've not put it there, but essentially if that's the line, then that is x0, y0, z0 is 1 point, and x1, y1, z1 is the other. So draw lines and you're good. Now, how do you get the lines, right? How do you get x0, y0, z0? Well, you've already done the math for that. We remember the math where we figured out the D30, that was the position of the end effector, but you could get the positions of individual links. It's all buried inside the DH table. So what you do is, just like D30, you find D20, D10, and then once you have those 3, you'll have the x, y, z positions of different points, and you can just join them. So the recipe is as follows. It borrows from what we've done so far. One is assign attached coordinate frames, which we've done. Find DH table, which we've also done. And then third step is compute A10, A20, A30, and so on. Okay, so we get the transformations from 3 to 0, 2 to 0, and so on. And once we have that, we find coordinates of of the joints. And as I said, this is all buried in the A's. It's as simple as this. For joint 0, we are going to assume that the manipulator starts off from 0, 0, 0. So that's the position. For joint 1, it's going to be A1, 0. It's going to be the fourth column, first 3 elements. So 1, 2, 3, 4. This is the Matlab command, which will give you basically this. Basically gives you, so you have 1, 1, 0, 0, D1, 0, 0, sorry, 1. That's A1, 0, right? And so this, what I've written down, is essentially this piece here. If you want D1, 0, you just write A1, 0, 1 to 3. That is the first row, second row, third row in the fourth column. This is column 4. And then joint 2 is going to be A2, 0, 1, 2, 3, 4, and so on. Okay? And then you just use the line command. Fifth step, use line command to join the joints together. Okay, so just keep drawing lines. Very, very easy. I'm going to show you MATLAB code, which will do that for 2 manipulators we've talked about. One would be this manipulator, the 3-link non-planar manipulator, and the other one was this 2-link manipulator, which we did in the first DH example. Just 2 links. It's all planar, so it can only move in the plane. Pasted, you do not have to do that. There's an easy way to get the output as a PDF file without copy pasting. So I'll show that, but first let me show you how to draw the manipulator. So first, this is the 2-link manipulator. What I like to do is I like to write the DH as a function. So this function is, remember, there are four transformations. There's a rotation about theta, d, and so on, which I wrote down and I generated A. I did not write that complicated formula. Instead, I just used the basic transformations. And this is just a function which I'll call again and again. So I just write a function, keep it aside. For the 2-link manipulator, which I will remind you of first, it is right, this one. Okay, remember this one, the first class, it's a planar manipulator. We're trying to plot this manipulator for different values of theta 1 and theta 2. Okay, theta 1, theta 2 is given. So let's go back to the code. What I do is, as I take the first, the DH table, the first row of the DH table, that was, believe me, that was what it was. We chose the length to be 1. I found A01. It's as simple as passing all the 3 parameters to the function which I just showed you. Then there's a second link, and so that link also has its own DH, which comes from the table. And as I said, you need to get the locations of each of those joints. So end of link 1 is simply A01, 1, 3, 4, the same T10 which I talked about a while back. And then A02 is A01, A12, so that's again 1, 3. So the position of the end effector is the A02. So D20 orientation is that. That's not what is asked. I'm just asked to do the plot. So line command, you can see I wrote X, Y, and Z. I want line width of 5, color of red for the first link. And the second link, I want it to be blue. Plot. Okay, so right now it's 0 and 0, so clearly the manipulator is along the x-axis, but I can change the angle. Let's do this pi divided by 3, and then that's 60 degrees, and pi divided by 2, 90 degrees, and run this. You see the manipulator is that. So 60 degrees for the red link with respect to the x-axis. The 90 degrees is with respect to the red link. The blue is at 90 degrees to the red, right? So it's 90. That's the red, that's the blue, 90 degrees. And you can do a bunch of other positions. The other manipulator I am going to do is the 3-link manipulator, which we just did. Actually, oh, this is not from today's class. It was also done last class. This is basically a screenshot of what I had. I'm just going to draw that manipulator. Yeah.
Where's the degree of freedom linked to?
You mean in the first one?
No, this one, like.
There's no L2 because it basically is D2. D2 is, this is a prismatic joint, so it moves. So it's just its position is determined by how much that joint moves.
So D2 is not fixed.
D2 is not fixed. So this thing, D1, theta 1, I put a star here. That is the degree of freedom. You change that by, if you have a motor, you'll be able to change that. D2 and D3 are the other things. So those are things you specify. Other ones are parameters for that manipulator. They will not change. And we are trying to make a plot of the manipulator when we change these 3 numbers, which determine the degrees of freedom of the system. So let's go back to 3-link manipulator. And what I did was the same logic. We have first line, second line, third line from the DH table, find the end of the links, essentially copy paste that code. I want to have the lines red, blue, and cyan. I also want to, now this is going to be 3-dimensional, it's not planar, so I use this command called view3, and this basically sets up this something called azimuth and elevation. If you do help view, it'll tell you more about it. But essentially you can view the 3 dimensions from different viewpoints, and that comes from using view3. So let's run this first. All angles, all distances are 0. So this is how the manipulator will look if you put everything equal to 0. So when you looked at the joint config, just the joints, it was not very obvious, but this is how it will look. And then you can change angles, let's say. So in this case, you got to change. Oh, my bad. I put. Is this right? I think I might have done an error here. Let me go back to this. Sorry, to this. T is 0. Alpha is 0 minus k. Okay, it looks good. So theta 1 I can change because that's the degree of freedom. Let me make pi by 2. I could change D2. I'd put 0.4. You could, if you want, you can put 0. And then D3 is other parameter. I put 0.5. Let me put 0.2. And run this again. Now you can barely see the blue. That's because that joint, it's moving, right? So it's 0, so you can't see it. The moment I change it back to, say, 0.2, you will see the blue. See it there. So it's basically a prismatic manipulator. If it's 0, then it gets blurred. You don't see it. Okay, sort of like a what do you call it? It's very difficult to give a prismatic example. There are very few degrees which are prismatic. Can't think of the back of my head. Okay, so that is about plotting. Any questions about plotting? I'll give you this code when you use it. You can do multiple links. What I was trying to get to was you can make Matlab generate a PDF file which you can then submit as your homework. What you can do here is, if you go to publish and you do this thing, which is in this folder which has these manipulators. You can see this 2-link PNG. I put that in a folder called HTML. So 2-link is here. This is a special syntax I used. It has to be in this syntax. It should be the name of whatever picture I want to get included when I publish. We'll edit the publishing options. So you can see by default it's going to output as an HTML. This is what if you want to take a code and publish as a web page. But in this case, I'm interested in making a PDF. So save it as PDF, and then I say publish. What it'll do is it'll actually execute the code, and then it'll make a PDF file, and that PDF is something which you can share. So I think it will pop up the PDF in just a bit. Okay, so this is the file which was generated by Matlab. It included the figure. It actually has this nice index. You can use that to navigate. Table of contents. So it makes sort of a hyperlink. I wrote it down to show you what's the effect of putting sort of section numbers, if you like to call them. If you want to put section numbers, like for example, section titles, then you need to put 3 percentage signs. Okay, that's true for C3. Can get rid of this. Okay, so that would be another section. It will, if you put a comment like this, that will show up just like a regular comment. See this percentage DH for link 1. It does not show that up as in a different font size. So the specify parameters was right here. So this is a way you can publish a code and you don't have to copy paste. It actually goes beyond just publishing your code. It actually publishes the results too. So if you keep scrolling down, this is the results, right? Position of end effector. That's what I wanted to print. The orientation of end effector. It then plots the figure, and your file is complete. So you show everything right from your work, your code, as well as the output in one click of a button. You could also do HTML if you wanted. You can do the same thing with the other file. Let's do plot 3-link manipulator. Let's publish it. So I executed it, and then it generates a PDF. So this is, oh, okay, so I forgot to make this as a PDF. I said HTML. So this is an HTML. See this HTML. So if you go to the folder, it actually created a HTML file. So if you want to publish this as a web page, yeah, so it looks much neater than PDF. Yeah, so if I wanted to change, I would go to the options and change the options to PDF, and I would get a PDF. And there are a bunch of other options that you can make a document file or whatever you want. Okay, is that clear? So that's an easy way to publish your stuff. Okay, any questions on that? Okay, so what I'll do is I want to cover a little bit more. And it's best motivated using our 2-link manipulator example. Okay, the end effector, this is where you'll attach the pen, say if you want to draw. We want to basically, let's call the end effector position to be XCYE. We've derived the formula for XCYE. So we've seen that XE is L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. and YE is L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Okay, so forward kinematics is what we've done so far. We are given theta 1 and theta 2 and we find XC, YE using 1. Okay, so that's something we've done, we've plotted. Also, the inverse kinematics problem, which is probably the more useful problem, is to figure out, we are given XC, YE, we need to find theta 1 and theta 2. The good thing about forward kinematics is that given a theta 1, theta 2, there's a unique XCY. Okay? The issue with inverse kinematics is that for a given XCY, you could have either no solution, you could have 1, 2, 3, and so on. You could have multiple solutions. So for a two-link manipulator, specifically, if this is a manipulator and if I give your XCY to be here, so and my hand cannot reach there, then that's an example where there's no solution. So you need to know the reach of your manipulator before you give it an XCY. There are some cases where there are two solutions for a manipulator. Let's say that I want my manipulator to go there. I could either go this way, or I could go this way or this way. So those are two answers to the same problem. So you could get multiple solutions. You could also get, well, in this case, if you rule out certain angles, you get one solution. But for a two-link manipulator, you generally get two solutions to the same angle, that and that. So the question is, how do you solve for inverse kinematics? Because most of your problems are fetch the glass or draw this. So you're given XCY, find theta 1, theta 2. For that, I'm going to introduce solving nonlinear equations, and this is something you've probably done in your numerical methods class. So let me write down here before we move on. Actually, let me write it on a new page. So issues with IK. I'll always refer to inverse kinematics as IK. We can have no solution. Example would be out of bounds. So if you want to go to this target, but if your manipulator is only so long, so you cannot reach. That's an example of no solution. The other example is multiple solutions. So you want to reach here, you can reach that point using two ways. One is this way, and the other one is that way. One solution, second solution. Okay, so I'm going to show you a technique for solving for the solutions, because we backtrack a little bit. If you look at this formula, if I give you theta 1 and theta 2, it's super easy to find xc and y because you just apply that formula. If I give you xc and y and ask you to find theta 1 and theta 2, it's less obvious how you can find theta 1, theta 2. In fact, for manipulators with multiple degrees, it's going to be a mess. It's going to be a sine, cosine, blah, 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 and it's going to be really hard. So the way you solve for the way they design manipulators, and most of the time since manipulators are doing this task, is to design manipulators which have a closed form inverse solution. So you can actually manipulate the equations, so you can write a formula for theta 1, theta 2, theta 3, and so on as a function of parameters. So imagine this, designing the manipulators to be able to do the inverse solution. But these days, since numerical solutions are fast, computers are fast, you don't have to design a manipulator which has a closed form solution. You can actually use numerical techniques to figure out the solutions to the problem. So there is a particular function in Matlab which I'll use to do this. It's called fsolve, and it solves basically the roots of an equation. So to motivate this, we go back to numerical methods where we talked about, where you probably learned about solving roots of an equation. You probably learned about Newton-Raphson, secant method, bisection, and so on. You do not have to program this in this course. There's a function fsolve which will do that for you. I think it uses secant rule or some variant of secant rule. So this is sort of refreshing you on solving non-linear equations in Matlab. Okay. Example is, if you have a function f of x equals x cubed minus 2x square minus 2x plus 3 equals 0, find x, right? You have to find x where that function f of x equals 0. So one way of doing this is to actually plot the function. Plot the function as the function of x. If you plot it, it looks something like this. So these are the three roots of the equation. Okay, so if you basically put this in a graphing calculator, you can maybe eyeball the values, and then you got to sort of iteratively get the answer to what is the exact value where it becomes equal to, f becomes equal to 0. In Matlab, we will actually not worry about graphing. We'll actually use this fsolve to solve for the roots. The syntax for Matlab, which you can find using help fsolve, is this. Equals fsolve. You give it the function, in this case f, and then you give the initial guess. So the various things in this Matlab command are, that's the solution, which case it will be one of the three. It will not give you all three solutions. In fact, you'll see that depending on initial guess, if your initial guess is close to this point, you'll actually get that. If it's close to this, it will give that. Sometimes it could give that one. So it really gives you one solution, it won't give you all. And you have to keep trying different guesses. So this is the initial guess. This is the function whose roots you want to find. This is the value at xf, which means that if you're exactly at the root, then f val will be equal to 0, and the exit flag tells you it converged or not. So it's important to know how confident is it in figuring out if it's gives you the root or not. So let me show you the code and let you go. Okay, I wrote a code which will solve that equation in Matlab. Did you guys use fsolve before in a course? Okay, that's good. Okay, this is my main file. this is my nonlinear function. I just wrote down the nonlinear function x cubed minus 2x squared minus 2x plus 3 in my main file. I actually also plot it. So x equals linspace, that plots the function f equals. So the first part plots the function and the second part solves it. You don't have to plot. I started with a guess, -5. There are something called options I did not talk about, but it specifies how rigorous you want the solution to be, how close you want it to be 0. Run this. It's thinking, shouldn't have taken so long. It's struggling, yeah. Okay, so that's the function which I drawn. It has 3 roots. It told me the exit flag 1 means it converged. This is the value. It's close to 0, very close to 0. It's 1e negative 13. The value is minus 1.3. So I started with -5, got minus 1.3. Let me start off with, say, 1. In fact, 1 is a solution, right? It'll actually give me 1. Let's see if it gives me 1. It says x equals 1. F value is exactly equal to 0. And then let me give something like 4. And this. Okay, this one converged, the f value is -10. 2.3 is a third solution. So you have to give initial guesses for it to converge. Now, one more thing I want to tell about Matlab. This is a fairly, well, it's maybe 5 years old feature. You do not have to run the entire code. You can run parts of your code. In order to do that, you need to put 2 percentage signs, and you got to do run section. So it only, let me do CLC. And then clear all, close all. Okay, now I'm going to run only this section. So you can see the yellow highlighting. It's only going to run the part in yellow. So I say run section, and only ran that. It did not solve the problem. Use fsolve. I can go down, click on this. It's highlighted. It's only execute that when I say run section. So now it solves the fsolve. So this is a way you can run parts of your code instead of running the whole code. Just another feature you might want to use. Okay, so that's it. I'll see you next time.